Now I want to tell you a little bit about atomic interactions, because everything I told you, I mentioned collisions and everything, but I did not define a little more precise atomic interaction. And so I would like to do, and I'm going to just jump through a few things so you can understand the concept of scattering length. I know again that many of you already know, but you know, it's never too much to review. So the most part of the gases we're working with, they are diluted. Okay, so the density is not that high. If the density is not that high, the most important effect of interaction is what we call two-body interaction. If you have too many particles, there is a good chance that three particles get together, and this is a process that's called three-body interaction. Okay, and three-body interaction is not like pairs of two. No, it's a complete different interaction. Okay, but here, in most part of what we're going to do, even though in some condensates, people are already seeing three-body types of effects and many-body types of effects. But normally, to understand most of what we're going to do is a diluted gas, and then the dominant process is two-body, two particles colliding. And then we have to understand this two-body type of effect. And two-body type of collisions, it's everywhere in the process of cooling. Like when you produce a MOT, a magneto-optical trap, you have a lot of collisions going on there, two-body collisions. When you have in the magnet trap, we already saw elastic and elastic collisions that are essential for evaporation. When you are in the condensate, even though there is no light, atoms are in the background, there is also interaction. In fact, most of the properties that we observe with quantum gas relies on interaction. So it's better to say a few words about interaction. And when we speak about interacting particles, we have to speak about potentials. And if you take two particles in the ground state, most likely the potential type you have is what they call van der Waals, at least at long range. And van der Waals, as you know, is this oscillating dipole type of force that appears and is present almost everywhere in nature, and is one of the main interaction responsible for the chemistry that we live. Okay, so imagine you have those two atoms coming together. The potential between those particles normally has this shape. Of course, most part of the atoms we're going to do, they share electrons. So you have to speak about the triplet and singlet type of state, right? And the triplet here is when the spins are parallel, or you are in a total one spin if it is a two-electron system, and the singlet is 0. And because of the symmetry introduced by the spin, as you know, the spatial form of the potential, which is basically the spatial form of the wave function, is different for singlet and for triplet. So if we imagine here, you know, and we go, the shape always has this very big barrier. It's a strong repulsive core, that's how we call. It has an attractive tail at long range. So when atoms are apart, they normally attract each other. When they get very close, they repel. And this potential is being well investigated, and everybody, and normally we have a leading term, which is one of our 6, but there are other terms as well. And we normally, the traditional van der Waals interaction is given by this term, and this C6 as being measured and calculated for many of the systems we're going to work with. And as you know, hydrogen has a small C6, and the alkalis have a big C6 because of the polarizability, right? So normally you see they interact a lot. And this here is giving in units of atomic units, that for C6 is the electron charge times the Bohr radius to the 5th power. And normally the other coefficients, as you can see, they are not so important. Remember, they are bigger, but they go with the larger power, so they just disappear almost. So this is normally the interaction between the atoms. And when they are very cold, when the momentum of those atoms are not so big, we have to come with the concept of scattering length. Because scattering length is a quantity that somehow resume all the interactions present in this system. So I'm going to fast show to you what is the scattering length that everybody going to speak about, and try to show why we can manipulate, as Vanderlei was saying yesterday, that using magnetic field you can go up and down and make positive, negative, and so on. So to tell you about the scattering length, we have to show some scattering. And the scattering problem in physics, you have an income wave. Here we're going to do all quantum mechanically, right? So you have an income flux and you have an outgoing flux. And normally we picture this in the following way. Imagine you have two atoms, and here I put v over 2 of velocity for each because I want a relative velocity which is v, just for my calculation here. So in fact, this is a wave coming. It's close to a plane wave coming. And encounter this in the relative motion coordinate. You have this plane wave coming, and then they collide, but the product of a collision can go everywhere. So normally we picture in the following way. There is a plane wave coming, and there is a spherical wave going. This is the typical scattering problem that we learn in the first course of quantum mechanics. But when the atoms are approaching, there is interaction. So imagine you have this plane wave coming, right? So the plane wave is coming at long range. One atom does not feel the other very much, so you have this type of oscillation. It's like a plane wave, a sine wave, or whatever. And then when they get together, they either accelerate if there is attraction, or they decelerate if there is repulsion. So if we see the outcoming wave, it is either a little bit advanced or a little bit delayed, right? Compared to the no existence of potential situation. This is what characterizes what we call phase shift. And most of you already learned that, and I even calculate phase shift from potentials, right? And so this phase shift, somehow if I look from far, the phase shift has to give me information about, as an overall, how was the interaction. Because if the wave is a little delayed, or if it's a little advanced, I can know if the potential is effectively attractive or repulsive. So the thing we're going to do is relate the phase shift with the interaction. And in the low energy limit, this relation gives me the scattering length. So the concept of scattering length is a concept that tells us about interaction, okay? Okay, but we have to write a wave for this process. So the wave that represents the system is a plane wave, which is the incoming channel, and is a scattered wave, which is the outgoing channel, right? And as I showed to you in the picture, the income is a plane wave, and the outgoing is a spherical wave. So, normally, the income wave, this is like sines and cosines, which is the plane wave. Now, the spherical wave, which is given by this, everybody had a chance to see a spherical wave already, either in optics or in quantum mechanics. So this is the spherical wave. But because of the characteristic of the potential, you don't expect the amplitude of the spherical wave to be the same everywhere in space. So you have an amplitude which is theta dependent, depending on the angle. This we call the amplitude of the scattering, right? So this is an easy way of writing things. And turns out that for very low energy, this F function, which is the scattering amplitude, is a constant. And I'm going to show you why it's a constant, at least very briefly. And this constant we call scattering length. It's A. But because it's independent of angle, right? So that's why we call S wave. It's no angle dependent. And if K is very small, because we are talking about small energy, right? The only thing that can be small is the momentum. If the momentum is very small, basically the exponential is 1. Right? So this function here at the low energy limit gets this form. So in the low energy limit, the wave function of this scattering problem is this. It's a function that extrapolates to 0 exactly in the internuclear separation that is equal to the scattering length. In fact, that's the way we measure. We go measure the wave and we extrapolate to 0. We see that in doing photo association, or there are techniques to measure this. Okay? So this is the scattering length. So the scattering length is in fact the scattering amplitude in the very low energy limit. Now, how is this scattering length connected to the phase shift? To do that, I'm just going to recall you that that amplitude of scattering is basically the differential cross-section. Right? I'm not going to give you detail in here because otherwise I'm not going to advance. So F to this amplitude square, and this can be a complex function or anything, right? As everything in quantum mechanics. Right? It can be complex, but when you go to measure, it's real. So this is the differential cross-section. And if this is a constant, bingo, you know, this is a constant. So I integrate in the angle, and I get the cross-section, which is only dependent on this constant. Right? So I integrate, if this is a square, the integration gives me sigma, and this gives me 4 pi. So the cross-section is completely related to the scattering length. And if we go a little further in this scattering theory, we can normally, when you solve the equations, right, for the scattering problem, we find we can express the amplitude of scattering in terms of polynomials and in terms of the phase shift and the angular momentum involved in this process, which is L, right? This is the angular quantum number. But if it is very low energy, K is so small, and remember, if I have a very low momentum, I can't build up angular momentum. If I have a very small linear momentum, I cannot build up. So it's S wave, there is no angular momentum. L is equal to 0 for very low energy scattering, because basically RK is the angular momentum. And I cannot build even a h-bar unit if K is very small. So as you know, I stay to 0. So this is what we call S-wave scattering, because there is no energy enough to build up angular momentum, right? So this is S, only L equal to 0 contribute, because it's very low K. Then the cross-section here is I just put L equal to 0, and I give this. And if I have a small phase shift, just expand this. And you find out, if you compare this with 4 pi a square, you can automatically get that the phase shift is basically the momentum times the scattering length. And as you saw, it doesn't matter the shape of the potential. Everything turns to be one number that characterizes the interaction. So we use that all the time because we are in this regime. So all the interaction is characterized by the scattering length. And the scattering length, if you have that potential that I just showed you, is a number, finite number. For one state, it's one number. But turns out that the atomic system is not as simple as a simple potential. You have many potentials there. And you may be facing a situation where you have potentials like this, right? Like the singlet and the triplet is an example of this. But you have more than that. You have a hyperfine. You have all kinds of energies there that provide you different potentials. So all kinds of interactions. So you may have, suppose you have a particle, forget about this potential here. Normally we have a particle coming here, it bounces and goes back. And then there is a phase shift, and then there is the scattering length. Right? This is what we call an open collisional channel. Comes and goes. But we may have what we call a closed collisional channel. Closed collisional channel means that particles cannot be in that guy in the asymptotic regime, right? I start there, I come, I may interact with everything, and then I leave. So if you have a situation like this, imagine that this is total energy, and my particles are colliding. They have translational motion, so the total energy is a little bit here. When this energy matches the energy of this closed collisional channel, right? Because particle cannot get in there. There's no energy. But it feels, because the quantum mechanics is made of a lot of interference. And then the existence of a possibility of a bound state here affects very much the way the particle interacts in this region. So normally when my translational energy matches this, I say I have a resonance. And people has investigated this in nuclear physics long time ago. The principle of Feshbach resonance is not from atomic physics, from nuclear physics, right? And so in this case, the scattering length and the phase shift and everything else is very much affected. It can go, it can have different signs because of the interference of this free channel, where the collisions are coming, with this closed channel, which is a bound state present in there. And because of those potentials, and this is called Feshbach resonance. So somehow the scattering can go very big because of this matching. And what's interesting here is that because I can use external field to put this level up and down, because of the Zeeman shift, or even the Stark shift, what I can do is do the following. I can come with a magnetic field and raise up or put down this whole potential here. And the levels goes together. So I have a way of tuning this using external fields. And this process, well, let me tell you, that's a second order process. Particles start in that open collisional channel, interacts with the closed channel, and leaves in the open channel. So you have two particles colliding that potential, and then they are intermediate. They feel that during the interaction, but they leave, they decay and leave in that potential that was the beginning. Okay? And this whole interaction makes the scattering length to modify the shape. In fact, when my translational energy is equal to that energy of that state, I have a singularity there. And this is what Kettley wrote yesterday. And of course, there are people that do this calculation very precise, considering all those channels and all the coupling and everything, and comes with theoretical relations. But they normally look like this. And I manipulate this guy. I don't manipulate this. What I make is this bigger or smaller than that, and that changes the sign. That's why you saw that dispersive type of curve. And you're going to see many of those during this school. Everybody got that? So this is the concept of scattering length, and that's how we manipulate scattering length. Okay? Okay. So normally, you can show that the scattering length can be written as a scattering length plus a term here that can be very big if I use a magnetic field as a tuning parameter for these levels. I've been very explain things so otherwise, but any book you take on scattering theory or in atomic collisions, there will be details on this, okay? And even I can follow, so I'm sure all of you can follow. Then people has measured scattering length. I'm going to jump to this, but this is to give you an order of magnitude for the values. This is in atomic units. Remember, atomic units for us in length is the Bohr radius, right? Which is about 0.5 angstroms or 0.05 nanometers. And you see there are systems with a huge scattering length and can be positive or negative. And that has very big consequences on the characteristic of the condensation. The magnitude, the size of the scattering length, as well as the sign. Okay? And then you have people measuring, and there are very nice techniques on collisions to measure this, and I recommend you if you want to learn about this. There is a review of modern physics that we wrote 6 years ago, I think. And it's a very thick paper. It's not the one I hand to you. And it's only about atomic collisions in the ultra-cold regime. So you can learn there what are the techniques employed to determine those things. Okay, so this is a kind of introduction to the atomic interaction, and everybody be speaking about scattering length, so it's better for you to know. Now I want to change topics and start to speak about Bose condensation, right? Because so far I only spoke about other things. And I had a vision of going very far and show to you the real necessity of a chemical potential. But this is very well explained in a book by Feynman, Statistical Mechanics, and I'm going to jump to that because I was going to explain how comes that we need the chemical potential and what is the physical interpretation of it. But unfortunately, I'm going to have to jump, but I'm going to copy and give it to you, and it's almost self-explanatory, this, and turns out that you can understand and you can deduce from statistical mechanics. And you know, statistical mechanics rely on partition function. Partition function is how energy can be divided, right? And so everything has to come from there, from that principle, from that key principle. And what I did is start with that principle, introduce to you in the context of quantum particles in a system, why you need the introduction of the chemical potential, which is this little number here, mu. Okay? But I'm going to jump to this, give you the copy, and I will be here the whole time, so you can come and ask me. But if we do that, we can come with an occupation number that Ketel already showed yesterday, which is, if you have particles, a number of particles in a quantum system, and if there are bosons, and Ketel said very clear that nature loves bosons. So if you are a boson, you are in good relationship with nature. So you can share space with your friends, you can share energy, momentum, and everything. Now, if you are a fermion, you are neglected by nature, right? So you are always alone, in the best condition with a partner. So, this is the... He said that, right? No? He said that. So it is true. He showed that most part of the isotopes are bosons. He showed that nature likes bosons. But the electrons are here, right? But they have charges, so. But the neutrons, they don't, right? Anyway, the fermions always get together to make bosons because life is more pleasant when you are among friends and sharing things. Okay, so doing this deduction, I can end by having what we call the occupation number, which is in a quantum system, each state characterized by an energy epsilon I have an occupation number. And this is, of course, if it is plus or minus here is what makes a difference, if it is fermions or bosons. And now I would like to give you 10 minutes of how, in a simple way, you can calculate things on a boson system, right? And I'm going to just do two things. First is the occupation. We have a number of particles there. Second, because I want to give you some macroscopic properties, we're going to deal with the energy. But as you saw, there are many things to be worried about in a boson system. So the total number of particles is normally or has to be, the sum of all the occupations. I have a number of particles in each state. If I add up everything, I end with my total number of particles. And energy is the same, but you introduce energy of each state in here. Turns out that we don't like to work in that way, or it's not so easy. And then we introduce the concept of density of state. Instead of having how many particles has this specific energy, I say, well, how many states I have around this energy? That's the density of state. And then I just say, well, each one has any epsilon occupation. And then normally introducing the concept of density of states, which is how many states are between energy E and E plus dE. I transform those sum in integrals. And to do that, I multiply by the number of states that you have in each interval dE, right? So I have this expression. But in doing this, as you know from principles of quantum mechanics, the density of states goes to 0 at the ground state. So when ρ is 0, I'm not considering that point in the integral. So I have to explicitly retain the particles that occupy the ground state. Which here, I'm going to say that the energy is 0 there. So this will be my starting point for energy. But that doesn't matter. You start the counting energy whatever you want. Okay, so this is the expression we have. And normally, the density of state depends on the potential, depends on basically the potential.
It depends on the dimensionality.
Oh, yeah, but that's involving the potential, right?
Graph sounds strange. How many dimensions you want?
No, this is 3 dimension. In 3 dimension, if you go to 2 dimension, like the density state in a free gas is constant. So doesn't go to 0.
If I remember, ρe goes to E squared in 3 dimensions, right?
Oh, that's depending on the potential if you have. You have a harmonic or... say again, ρe goes to E squared. Yeah, and goes to 0 when E goes to 0.
That's the form of the graph.
Oh, no, the form, I don't know what potential I have. This is just a... this is just to show that goes to 0. Okay? The shape here, you see, is so imprecise. That's why, it can be this way, it can be root square, right? It can be anything. Depends on the confinement. So when I do that, I'm going to jump in this part. In cooling down the system, what's happening is that the first part of the integral, oops, I have to go back here. This first part of the integral, I have to say this, right? If I look at the occupation number, it normally has this shape and diverge. If you remember the occupation number, which is 1 over E to the epsilon minus mu, it diverges when you go to mu. But turns out that mu, which is the chemical potential that I should explain and I didn't, is not a state of your system because we can show that's negative for a boson system. So the system stops here. If I see the occupation number as a function of the states, it stops here. It would diverge there. But as I cool down, this point starts to approach to here and eventually became the ground state. So at that point, the population diverge. You understand? Okay, so normally we say that Bose condensation will take place when mu became the value of mu became a value of the real state of the system. Anyway, so I have those integrals. This is just to show to you the way we can calculate things. And this is normally very small. This is basically 0. Until one temperature, that's the temperature where mu comes and meets the ground state. In that case, this starts to build up. And the way that this build up follows this relation. Okay? So normally this is basically 0 for temperature above critical temperature and is less than it builds up as an order parameter in a normal phase transition below the critical temperature. Yeah, because it's basically 0 and then suddenly appears, right? So The fraction of particles in the ground states is a kind of order parameter in this transition, right? Like the magnetization. How we calculate the density of state? Well, we go to the phase space, and as you know, for a given energy interval, the density in phase space, the area in phase space, or the volume, is related to the number of states you can have. So basically, the density of states is this integral here. So I consider in the phase space, and the possibility of occupying the phase space for my system is given by the energy, or the Hamiltonian. And if I vary my energy by d epsilon, I have this area here, and this divided by h cubic is the density of state. This is very much used in thermodynamics, statistical mechanics, right? Statistical mechanics is basically how you occupy phase space. This is the main principle. And if you do that, you can work out this energy, transform the units. Instead of expressing P and R, you expressing energy and R. So you come with an integral that's the density of state for any potential is given by this expression. So giving a potential, you determine the density of state. You determine the density of state, and the integral has to be done, of course, in the volume that this system can be accessed. And that's depending on the energy. So normally, if you forget about P, you make the energy equal to the potential. This provides you what is the available volume in phase space, in the coordinate, in the real coordinate for this particle. So normally we do that, and we have many examples like the box. If you do a box, the density of states goes with the root square of the energy. You do all the integral, and you find out that there is a point where that number starts to grow, and normally the temperature when that happens is when you have a 2.612 in density of phase space. And if you look what's happened, this fraction of particles is nothing, and at the critical temperature grows up very fast, and following a law, and this exponent depending on the potential too. Because as you saw, depending on the density of state. So for a harmonic oscillator, it's very nice because we can calculate, and how you find the critical temperature, you just make that integral and set the fraction of particles in the ground state equal to 0. You can get the critical, and the critical temperature for a harmonic oscillator that contains any particles is given by this expression. And the fraction grows below the critical temperature, following a cubic law. Remember, the box was not cubic, was 3/2. Huh? And we can do everything, and everything is done in this review I gave you. If you consider a power law potential of any kind, you can just generalize and find out critical temperature in terms of this, and you can find out this population fraction in the ground states below the critical temperature in terms of this parameter. And this parameter is basically related to the...
I missed something, sorry.
You missed something.
Okay, what TC is that? What transition you are...
It's the point where the population accumulates macroscopically in the ground state. Okay? Oh, that's the Bose condensation, right? Yeah. Is that from that point on, population grows in there. You understand? Yeah. I'm going very fast here too because I want to reach the other part. Maybe I'm not doing a good job here. Do I need to go back and then? No, it's okay. If you make a P, L, and Q goes to infinite, you recover what? If a P, L, and Q goes to infinite, what is this? It's a box. It's 0 everywhere and goes to infinite when X just pass A. So this is a box of volume ABC. And if those guys goes to infinite, of course, this goes to half. Eta goes to half. And remember, the box was 3/2. Right? They're growing. So everything is very consistent here and everything. So this is expression of a critical temperature for any potential that is like a power law, and this is the law of growing the population in the ground state below the critical temperature. Okay. And we can use this and calculate a few thermodynamic properties like heat capacity. It is a macroscopic property, heat capacity, right? And you just integrate, and then you investigate, and has this nice shape. Remember, the critical temperature is the point where mu goes to 0. Mu is negative, and as the temperature decreases, approaches 0. When it reaches 0, and that happens in a finite temperature if the number of particles is big. Normally, it should be infinite, but, right? As Kettley said yesterday, 1,000 seems big enough.
So the fluctuation
10,000 even better.
so much important.
No.
You are far from thermodynamic limit for sure, but
Well, why?
if you have
Because the chemical potential goes 1 over n. So if it is 0, or if it is 10 to the minus 3, seems that the system accumulates everything and shows the phase transition. Because Bose condensation has been observed for 1,000 particles.
The partition function can be given as a sum over the states, and then you can include the next term in the states, and then you get this finite size effects that you're talking about, that will be neglected in the infinite particle limits.
Yeah. No, that's right. In fact, if you look in the little booklet I gave you, there is a final number of particle analysis. You can see the corrections that has to be introduced and everything. Okay. Finite size effects. Yeah. So this is a kind of overall, description of this. And so this is a kind of integral that's easy to make. You can find the heat capacity. It can have this shape, or it can have this shape, depending on the potential. And this is expected, right? Because what is heat capacity? Is the ability of the system to take energy from outside. And if you have a potential, depending on the shape, particles has to work against the potential to build up energy. So somehow it's very much expected that the heat capacity will depend on the potential you have. This is ideal gas. Huh? I explain interaction, then I come to the ideal, and now I go to the interacting Bose gas. And very interesting that depending on the power of your potential, there are a class of potentials depending on this eta, which is the sum of the inverses of the powers, that you have discontinuity in the phase transition, in the heat capacity, and for some numbers you don't have. And if you remember Ehrenfest kind of classification of phase transition that nobody uses anymore, right? Now is Landau kind of classification of phase transition. But if you remember the old way, that means changing the order of the phase transition. Well, low dimensions, I'm going to jump, I'm sorry. But you can have Bose condensation. Considering ideal gas and the simple analysis I'm making, you can have Bose condensation in 1 and 2 dimension. No problem. You cannot have in a homogeneous potential, but you can have in a non-homogeneous potential. And it's very interesting that anything that confines in 2 dimension allow you to have condensation. Now, in 1 dimension, you need a specific class of potentials to have. Okay? And I remember very clear reading papers that interactions in 1 dimension makes the same effect. So you start to have a possibility of Bose condensation in 1 dimension. But Kettley said that, no, that's not the case yesterday. So I endorse Kettley, of course. Now, what's happened if I have a potential? And what's happening with the spatial density, right? So let's calculate. The spatial density is the occupation number times the wave function square, and add over all the states. But I can do that in phase space too. If I go to phase space, right, the number of particles in some states are given by this term. If I divide by the volume, I have just the density. I have the contribution of the density due to the 1 energy or 1 momentum. If I sum over all possible momentums or energy, which means this integral, I calculate the spatial distribution of atoms in any potential. And if you do that for a, you choose what you want, for any potential. You can carry on this calculation, and I'm going a little fast in here, and you find out, but because you introduce that integral in phase space, again, the momentum 0 goes to 0, right? In this integral, when p equals to 0, this goes to 0. So when I do this, I'm leaving out the ground state. So I have to add that. And when I do add the ground state, well, this is an easy calculation to do. You exchange the integral by sum, and there are all geometric type of series you can analytically sum, and you can get an overall density profile which shows that at the critical temperature, there is a jump proportional to root square of n. And that's the jump that you see everywhere when the condensation happens, right? At the center appears that big peak due to the accumulation in the ground state. Again, I'm going fast to this because I want to go to the other parts. Okay, so this is the Bose condensation introduction. And now I would like to speak about interactions because we treat ideal gas, ideal system. But interactions are present. And normally to introduce the interaction in our relations, we put a term here that's proportional to the density. So it's like in each point, particle is filling the average field of the neighbors. No, wait. This is just the introduction of interaction. This is the energy of one particle in this system. If I have interaction, I can add this term. Right? What? This is a main field. Yeah. Right? So if I put this term, this somehow represents the interaction. Whatever the density is higher in space, interactions play a more important role. And then I can use that semi-classical density that I calculate and come and even calculate for you the corrections that any potential you have due to the interaction in this building up of the ground state or corrections in the critical temperature, and they agree more or less. It's not so bad. But we want to go further with this. When I did this, I put here gamma, right? Gamma somehow represents interaction. And interaction in the ultra low temperature means what? Scattering length. So gamma is related to scattering length. So let's find out who is gamma. And to find out who is gamma, we're going to do a small calculation here. We're going to imagine that we have a contact type of potential, delta potential, between the particles. And we're going to calculate what is the energy per particle that this potential introduces. So you just do the integration, right? You integrate in density. Imagine you have one particle here, right? Well, one particle somewhere here in a position R1, and it is surrounded by particles which coordinate R2. And if I integrate this, I'm getting how much energy per particle I have due to the interaction. And this is easy to do. Delta function is always easy to integrate. And you get that the energy per particle is half of V0 times the density. Okay? And what I put there as gamma is basically the energy per particle. So, gamma times n is how much energy per particle interaction is adding to the system. So this has to be equal to half of V0 n. V0 is that amplitude of the potential, of the contact potential. So I end up by having gamma. And V0, this is a delta potential. Everybody knows how to calculate phase shift and scattering length. It's in any book of quantum mechanics. And the relation between the amplitude of the delta potential with the scattering length is this. So I end up by having gamma. So gamma is proportional to the scattering length. Okay? And then I can rewrite all my expression, and the corrections come as powers of scattering length divided by de Broglie wavelength. Okay. Okay, but this is not enough. This is just a very simple approximation. We want to go a little farther. And then comes the equation of Gross-Pitayevsky. And this equation is basically on the spirit of the interaction. You already know that if I have interaction, and this is for 0 temperature now. So if I have a system that is described by, each particle is described by a wave function, phi squared is like the density there, times the number of particles. So this A will have the number of particles in it. So, this is the new Hamiltonian if we have interaction. But of course, the wave function of my system, if I have any bosons there, right? The total wave function is the product of the individual wave functions. Then I'm going to take this. This is just the energy. It's not the wave function or anything. I take this and I create this functional. I say, well, each particle has this wave function. So let me calculate this. This is energy. May not be the energy of the system, but it's an energy. And then, as you learn from variational principle, I try to minimize this functional. Yeah.
In your last transparency, what happens in T equal to C for that region?
What term?
In the previous case, you had 0, right?
Oh, okay. So what I do here is the following. I calculate gamma, and then I come and I say, look, why I don't consider this as an effective potential? And then I do the semi-classical calculation again. And I can come with all the corrections.
Okay, but at T equals TC, before you had
Oh,
for the region, now,
yeah, at T equal to TC,
yeah.
what's happened is the density has a big jump. Ooh.
But you got something negative, right?
Let's see. Yeah, you see, the correction on the critical temperature or in the order parameter here on the population of the ground state depends if it is attractive or repulsive, the potential. If it is attractive, it's like in this approximation, particles get together, the effect is like increasing the density, okay, in this system. If it is repulsive, it's like particles getting far apart.
Okay, what I'm saying is that N0 over N is minus gamma A at T equal to C.
N0 is equal to 0. And then I have a correction here. So if I make this equal to 0, I can tell you what is the new critical temperature in terms of the ideal system critical temperature. So maybe this is the confusion. TC0 is the critical temperature of the same system if you make gamma equal to 0, okay? Right? Don't sleep. I have a very good joke, and we're giving out a prize for whoever stays more awake. Did I answer the question? Okay. So now what we're going to do is build up an equation in a more serious basis. So I wrote a Hamiltonian, and why I did that simple approximation before is to tell you that adding here a term proportional to the wave function square is natural. It's like saying that interaction goes proportional to the density. Right? Because wave function square comes to be density. And in this system where all the functions will be the same, if I multiply by the number of particles here, minus 1, but I take the minus 1 away because n is much bigger than 1, so this basically gives the density there, in some sense. Okay, but I want to solve, I want to get this wave function. So I just take now this functional, and I minimize, but I cannot minimize in any sense. I have to minimize this with a constraint. And the constraint is that the total number of particles is in my system. And variations on the energy has to be related with variation in the number. That's the only way of varying energy. So this is a constraint. And if I minimize this, taking this constraint, using Lagrange multiplier, that I'm sure you're very familiar with, or if you are not yet, it will be very soon. If you are undergraduate, sooner you're going to have to deal with this guy. Then I come with an equation, which is called Gross-Pitaevsky equation. What I want to point out for you is that the Eigen, normally this is called nonlinear Schrödinger equation. I only put in the time-independent one, okay? But the eigenvalue of the Gross-Pitaevsky equation is not the energy per particle in your system, it's the chemical potential. They are only equal when there is no interaction in the system, as I'm going to show to you if I can go through. So this is the Gross-Pitaevich, and everybody uses. It's still mean field approximation, right? And instead of treating this Hamiltonian, or instead of, forget about this term, and this will be the energy of your system. But because of this nonlinear term, the eigenvalue of the Gross-Pitaevich is not the the energy per particle in your system is the chemical potential. But of course, once you have the chemical potential is the derivative of the energy with respect to the number of particles. If there is no interaction, of course, this is E is equal to, if there is no interaction, E is equal to any mu, because mu is the energy there, as I showed before, when you condensate. Then the derivative gives you mu. But if there is interaction, this is not true. This does need to be true. Okay? So once I have the wave function, then I can calculate the energy of my system, going back to the functional. And of course, A is a term very similar to the one I did in a very hand wave type, which is proportional to the scattering length and can be positive or negative. So in fact, this equation here is the equation that describes the interacting Bose gas, and everybody uses.
It's not phi 3?
Oh, sorry, it's missing it's not phi 3. It's phi squared times phi, times phi. It's a mistake. Sorry, you have to add here a phi. Thank you. It is right there. Yeah, sorry. This is a night problem. Not eating enough, this kind of thing. Yeah, you start to eat the functions if you're not eating enough. That's why we have this dinner tonight. So you don't eat functions, you eat meat. Okay, it's missing a phi here, sorry. But so the Hamiltonian that we're going to deal with is this Hamiltonian that I give you here, okay? And of course, when you're going to do the equation, you multiply this. If it is a time dependent, then IH ddt of phi is equal to H phi. You know this very well, right? A lot of people in this room work very deeply with Gross-Pitaevich, so I have to be careful. But Gross-Pitaevich is nice because even experimentalists can understand. And better than that, in some situations we can solve. Isn't that right? Okay, so we have the equation. Now we have to solve. And there are approximations that we make to solve this equation. The first one is the Thomas Fermi. What is Thomas Fermi? Well, I get that equation. Remember, the Hamiltonian has a p squared divided by 2m, which is that Laplacian. And if the system has a strong interaction, if this term is very big, kinetic energy is somehow not important. So, cross that away. The equation I end with is this one. And this is called Thomas Fermi approximation. It's in a regime of very strong interaction in your boson system. And once I have that, this is the equation, right? That I have. This is the chemical potential. And this equation, everybody can solve, right? This is an algebraic equation. You eliminate this, is phi squared is equal to this. And this cannot be anything. There is a moment where this goes to 0. So the wave function goes to 0 there. And the wave function square goes to 0. And as you know, this cannot be negative. Stops there. So that's why Kettle made that plot, that in a harmonic oscillator, the wave function is not the Gaussian anymore, but is 0, builds up a parabola, comes back to 0. Because if the potential is a parabola, the wave function square, which is the density, follows exactly that. There is a boundary where the particle exists, and when this is 0, which means the potential is equal to the chemical potential, you determine the boundary, the volume that particles can live in this approximation. And outside this region, the wave function is 0. So, let's solve this for a harmonic trap, which is the most popular around. If you have a harmonic potential, then U is a half of m omega square r square. And of course, the integral has to be 1, right? This is a wave function per particle, for one particle. Would be n if it is the total. Then where is this space that I have to integrate? I just make the potential equal to mu. Then I get that the volume that's occupied by the particle is given by this radial. So my integral doesn't need to go from 0 to infinite. Goes to 0 to r, because outside r, the wave function goes to 0 anyway. So when I do this integral, which is just substitute the things here, is trivial. This is the function that I did before there. You following, George? Okay. So when I do this integral, the only thing here will be mu. And I can determine, remember, A has n on it, the scattering length. And to simplify things, I'm working everything in terms of the characteristic length of the harmonic oscillator, which is this L. So mu, for this system, is given by this expression, just by doing this integral here. So I have mu, okay? So I have mu. This is the chemical potential of my system, which is a kind of eigenvalue in the Gross-Pitaevsky equation. But I did in this approximation of strong interaction, which is, you don't need to do numerically and everything. Now, since mu is defined as the variation of the energy with the number, and I have mu there, this should be in the same way. See, mu here goes with n to the 2/5. Then I ask, what is the function which derivative give you n to the 2/5? You find very easy. Has to be n to the 7/5, because when you take the derivative, give you 2/5. And there is a constant here that's very easy to determine. So this is the energy of my system, which is completely different from the chemical potential. Okay? So that's somehow is the energy per particle I have in my system that would be the eigenvalue of the real Schrödinger equation. Everybody follow me?
So first, you took the Gross-Pitaevsky equation.
Yeah.
You put an eigenvalue that you put.
No, I didn't put anything. If you solve the time-independent Gross-Pitaevsky equation, what you're getting as eigenvalues is a nonlinear equation. But what comes out is the chemical potential. Okay? That's what I want to say. And then I approximate. I say, throw away the kinetic energy, and I solve the problem for the harmonic oscillator. And I show to you that chemical potential and the real energy per particle in your system are different. In fact, the real energy per particle in your system is 5/7 of mu. It's near, but it's not exactly. Right? So, normally the wave function in a system, like in a harmonic oscillator, we'll have a Gaussian type profile. But in the Thomas Fermi approximation, it starts here and dies here. And this is what people observe when they produce Bose condensation with a very high number. Because if you have a very high number, the term A in the Gross-Pitaevsky equation is much bigger than the other terms. And you can do this approximation. Okay. Oh, no, I'm going to jump this. That's the only way of solving Gross-Pitaevsky equation? No. There are other ways, and we like very much. Me and a few friends around here, girls and boys. The renormalized perturbation theory. And if you have any question, you can ask Lillian and Edmir. And what consists this approximation, in my point of view? Maybe their point of view is a little different. But suppose we have a harmonic oscillator, and we're going to write down the Hamiltonian, which is the Gross-Pitaevsky equation. And here, I'm going to, this is the equation, right? Then I'm going to just normalize everything to get rid of units. So remember, instead of A, going to appear a G, which is what we call interacting parameter. 5-4. No, Hamiltonian is 5 square. This is just the Hamiltonian. Okay? Then the Hamiltonian is just rewritten this way, okay? So lambda here is the normalized frequency. I just divide everything by those units. So I'm expressing energy in units of h bar omega and length in units of the characteristic harmonic oscillator length. Okay, so this is Hamiltonian, and I want to solve this. So the question is, how much different this is from this? This is a simple harmonic oscillator. And you're going to say, oh, it's very different. Here, we don't have this term. But maybe it's possible to adjust this parameter, which is related to frequency, to compensate the interaction. So what we do then is the following. We know the solution for H0, which is a harmonic oscillator. Right? Just a harmonic oscillator. So we solve this. We know the solution. Then we know that the two Hamiltonians differ by this amount. And then we calculate what is the variation of energy to this variation, like we do in perturbation theory. Then we correct the energy, and then we take the derivative of this energy with respect to B, which is basically the frequency of the ideal harmonic oscillator. And then we fit back. So we find the best B, we fit back and keep going. So this is a combination of perturbation theory and variational principle. And you end, when you minimize and you get the best you can, you have the eigenvalues of your problem. Because this is real energy. Because it comes from the sandwich here. Okay? So that's another way of solving Gross-Pitaevsky equation. And when you do that, you can find, for example, the ground state energy of your system. If you have some number of particles, remember that G is proportional to A, which has the number of particles in it. If G goes to 0, of course, there is no interaction. You have to get as energy 3/2 of h bar omega. Now, let's, as an example, consider the case where A, the scattering length, is negative, which means an attractive system. If you have an attractive system, as I showed you yesterday, the system is going to present instability. And if you do this calculation, and I had a student, Alex Gama, which is now in Bahia, that did a thesis on this. If you solve, suppose that G is negative, because the scattering is negative. And then you solve the problem, and you start to vary the number of particles. Suddenly, you get a complex eigen energy. And you all know what means a complex energy, right? Means an unstable system. And this, in fact, was measured by Handy-Hewlett. Handy-Hewlett was able to produce a Bose condensation with lithium-7, which has a negative scattering length. And what he found out? He found out as he builds up the condensate, suddenly this system collapses. So the condensate is stable up to a critical number. And then it collapses. And then we ask the question, how can we find the critical number? Easy. Solve the equation and ask the question when the energy became complex. At that point, you find that you have a critical value for this, when that became complex. And if you convert back in numbers, you get the maximum number you can put in a condensate with negative scattering length that still makes the condensate stable. Above this value, it collapses. So what Handy observed was like you build up a condensate, so you accumulate particles and suddenly, choop. Okay? And of course, if you have the eigenvalue, it's complex. The complex part gives you the lifetime. So you can even calculate how long this will live. And turns to be a few milliseconds, and this number turns to be close to 1,000, which agrees quite well with experiments. Okay? So, negative scattering length is a problem. Maybe it's good to make molecules, but it's not good for having a condensate. Maybe you make a molecule and the molecule will stay there because molecule to molecule will have a positive kind of interaction. But if you have a negative. So, this is basically, it's not the end. Don't get happy yet. So this is, now when you hear about Gross-Bitaevsky, Thomas Fermi, I know them. A lot of you know very well this. Some of you dream with this all the time, right? But for us, it's nice to know where is that. Okay. Now, for the last minute, I would like to give a few things that I think will be important for the other talks. And one of them is Bose condensation in a lattice. And we're going to do a problem here. I was going to give you problem sets, but that I'm doing myself. I'm a good teacher. I give you the problem set and I solve. And the first problem we're going to do is, let's consider we have an optical lattice. Remember I put a picture yesterday? Is that the configuration of potential wells distribute in 2 dimensions? And we're going to fill it up, this lattice, but we're going to fill it up in a very specific way. We're going to put all the particles that we can in a ground state. Okay? Remember, I have multiple wells. They have energy states. So all the particles are in the ground state of each well. Do you understand? Okay, then I leave there. Now I'm going to adiabatically turn the lattice down. The question is, what occupation number for the lattice I need to have so that when I destroy the lattice, I end with a condensate? Because normally what people do is produce a condensate, drop in an optical lattice. So the particles are so cold, they go to the ground state. So I have this multiple well, and all the particles are in the ground state. Now I want adiabatically remove. And the question is, do I always end with a condensate? So let's answer this question, right? So this psi is the occupation of the lattice. If it is 1, means I have 1 atom per site of the lattice, per potential well. If it is less than 1, means that the lattice is not complete full. It's partial empty. Everybody's following me? Say yes. Okay. Remember, I have a present here. I can't say what it is. It shakes. Okay, so let's do this calculation. Because I'm sure that half of the talks will be in lattices from today on. And it's nice to know what is the occupation, what is this, when I have, when I don't have things. So this is a good exercise for us to remind things.
There is no more than 1 atom per site?
No, in my situation, I have, filling up the lattice is like 1. Okay? Of course, in some situations you can put 2, but
Okay, but the situation is
1, at most 1. I consider a lattice that is complete filled when I put 1 atom in each site and 0 complete empty. Okay? Now, let's remember what it is adiabatic. Everybody knows what's adiabatic. What's adiabatic? That's when the entropy doesn't change, right? This is adiabatic in the thermodynamic sense. So, okay, just keep that in mind. Now we're going to take a lattice, and we're going to say, in this lattice, we have P available lattice points. And we have an occupation, which is psi. So the number of sites that are really occupied is psi P, right? Because psi is the fraction that's occupied. Okay, then I'm going to ask the following question for you. What is the entropy of this lattice occupied with a fraction psi? And if you remember principles of statistical mechanics and thermodynamics, you have just to count the possibilities. You just go and count. I have p sites available, and I have psi pi, psi p objects to distribute in these boxes. Everybody did that once, I'm sure. Even in high school we do that. How many red balls I can put in so how many configurations? If you do that, that's the configuration number. The entropy, thanks to Gibbs, is this relation. And then you just write this, calculate the entropy, and this entropy depends on the occupation number, of course, or the occupation fraction. This is a straightforward type of relation, right? I mean, this is permutations. Combinatory analysis, right? So then I calculate the entropy here. So I have the entropy. And the entropy depends on the number of sites, of course, but depends essentially on the occupation fraction. And I'm going to do some approximations like, oops. Oh, okay. So let's keep this here. Now, yes?
How many sites do you think you have?
P.
Right. But as a number?
Oh, that's depend on the size, but you can have many thousand. I mean, I don't know. Is it normally the distance between is typically on the order of the wavelength of light, because lattices are created by interference of beams, right? But so you can have many lattice points, yes. No, and normally you can drop thousands and thousands of atoms in those lattices, and you do all kinds of experiments, as you're going to see in the other talks. So, but now let's see a free Bose gas. Suppose I have a free Bose gas. What's the entropy of this free Bose gas? This is in all the books like Huang, Landau, Patria, Heights. No, what's the one we use in São Carlos? Heights. Heights is the electromagnetism book. Right? Jesus Christ. Okay. Sometimes you have to shake to accommodate the lattice points. So now, if you imagine a free Bose gas, this is the entropy. I'm not gonna. This is everywhere. You can calculate. So if I have any particles and I'm below the critical temperature, this is what I have. Okay? So this is the entropy of a free gas, and I calculate the entropy of a lattice. If I do adiabatically, when I finish my lattice, what's the entropy of the system? Has to be this. Right? If I end with something different of this, I don't have a Bose condensate there. Of course, we're not taking into account interaction. This is a hyper-diluted gas, because the interaction is not the point. The occupation of the lattice is the point. So remember that the number of particles is basically the psi times p, because it's how many particles I have there. I have p sites, a fraction psi occupied.
That number is some universal number?
What number?
1.2.
Oh, it's some approximations, but it's basically, yeah. But I took constants and I put, because otherwise I can't deal with the other expression. I cannot make a identity. That's why I gave up all the possible constants there. It is.
But it not depend of the
No, this is, no, it's a free gas. So you do in a box and then you make the box go to infinite. Okay? So this is the number. Remember, then I'm going to substitute. So this is the entropy of a free Bose condensate gas. This is the entropy of lattice. They have to be equal, because if I do adiabatically, entropy is preserved. So I just solve graphically. The optical lattice has this entropy. Of course, if it goes to 1, as you know, occupation, entropy goes to 0, right? And if you have 0, also is 0. If you have only one possibility, logarithm of 1 is 0, entropy is 0. You all know that. Then I just cross with the free gas. And there is one point here, which means 0.54 or 55 is about. So, if I have my lattice more than half occupied, when I adiabatically remove it, I end with a condensate still. If I have less than that, I have a cold gas, yes. Maybe quantum gas, yes, but not condensate, right? Okay, this is first exercise. Let's go for the second exercise because I said nothing about fermions. And you know, they exist. Nature is not so kind for them, but they exist. So what I want to do is calculate the Fermi energy. Because again, half of the talks you're going to see from now on, I'm going to speak about Fermi energy. Yes? Yes, please. Microphone. Oh, but the tape can't.
So if you have a lattice with each atom, one atom per side, okay? Then you know that starting with the BC, you have a Mott insulator. And in this case, you have that the fluctuation in phase are much bigger because the fluctuation in the number is almost 0. So this is almost related to what you've shown. It should be related in some way.
Boy. I don't know if the phase fluctuation will be related to the entropy I calculate. It eventually can, because once you have a thermodynamic function of the system, you can recover the fluctuations, right? So in some sense, I think if I express well the entropy in terms of the thermodynamic variables I choose here, I can recover, and probably they are related somehow. But this is a kind of straightforward calculation. Just show that to keep the entropy, if you really do adiabatically, you need to have a minimum occupation number. Otherwise, you don't end with a condensate at the end of the process. Because normally they produce lattice, and they study, and then they destroy the lattice and investigate. Some experiments are done that way. And we just want to know that if the occupation number is not right, then you may end with something different. Okay? Now, let's go to the fermions. I want just to estimate the Fermi energy to show you, compare with the bosons. So, Fermi energy, as you know, if I have a box, I just put all the levels, and I put 2 particles in the box by Pauli principle. And when I end my any particles, that energy is the Fermi energy. And this is also calculated almost everywhere in the world. If you can get a quantum mechanics book that doesn't have this, I give this present, which is here. And it's for the one of you. Okay. So this is normally what we do is we know the relation of energy. We start to pile up particles, and we end with this Fermi energy for a box. Okay? Now, box, we don't have box in the lab. We have harmonic oscillators. So let's go for a harmonic oscillator. That you may not find so easy, the Fermi energy for a harmonic oscillator. But maybe there are around because everybody works harmonic oscillator. I'm sure that the experimental groups or the theoreticians know very well this. So let's consider harmonic oscillator. This is the energy of the harmonic oscillator. And I'm going to just normalize energy in units of h bar omega, because here, energy is just the addition of numbers. Okay? So energy here will be 0, 1, 2, 3, 4, because I normalize by h bar omega. And then the question is, if you have this energy, what is the Fermi energy for a n-particle system? You have to add up. But now it's not that easy. Suppose you have an energy E. You may have many possibilities of states which have that energy. So suppose I have E. Remember, E now can be 1, 2, 3, right? So I have a E00 and NX, NY, NZ are the quantum number for the 3 direction. I'm doing 3-dimensional. But can be E minus 1, 1, 0. So you can just list all the possibilities, right? And you can count. And what's very interesting, when you do this counting, you end that the number of states for a given energy E is just this series. Is the sum from 1 to E of I plus 1. And everybody can do this series. So you do this series, and then you come here, and you find out, there is some approximations, and you find out what is the Fermi energy. This is for a harmonic oscillator. I put here the critical temperature for a boson system. Fermi bosons are very different. If I define a Fermi temperature as the Fermi energy divided by K, turns out that the Fermi energy and Bose critical temperature, they are very similar. What's very interesting, they scale the same way, so shows that the scaling of the energy and the temperature is just a property of the potential. But the root cubic of 6 is like what? 1.5 maybe. And this is 0.94, so the Fermi energy, and if we can call a boson energy, a Bose energy, which is the critical temperature, are very close. So to reach the degeneracy in a Fermi gas or in a Bose gas, you have to reach almost the same temperature if you have almost the same number of particles. That's interesting. Nature was bad to fermions, but not that bad. Make them to be almost equal on the temperature scale. Okay. Now, in this calculation I did, it's very easy to introduce an anisotropy, and you show that the Fermi energy scales with the anisotropy in the same way. And what is this? Oh, we're going to jump all this. Sorry. Where is my last part? Oh, here's sound. Ketel already spoke about sound velocity, and I'm going to speak more, so let's give up that. We heard yesterday about healing length, and I just want to show what I think it is healing length, okay? So healing length is the following. Let's consider a Bose gas in the Thomas Fermi approximation. Very strong interaction. You know, we saw that the wave function comes and goes to 0. Boom. Because it's the mu minus the harmonic oscillator. Goes to 0 sharp. If it goes to 0 sharp, what is the... Oh, this is a continuous function. Wave function never is discontinuous. Don't worry. But the derivative is not continuous. And worse, the second derivative is not continuous. That creates a problem for us, because the second derivative of the wave function is basically energy, momentum. No? Momentum squared is the kinetic part of the energy. So, if I have a divergence on the second derivative, I have divergence on the kinetic part of the energy. Right? So that doesn't seem right. And in fact, this is just an approximation. Wave function never will do that. There will be a length where the wave function going to smoothly go down. And this region, this length, this characteristic length, where the wave function goes smoothly down, is the healing length. And we can calculate. Because we know that at that point, that situation, the energy is not infinite. The energy is about the chemical potential. This is the energy available there for per particle in order of magnitude. So we can estimate what is the healing length. And then we just take this, which is given by this, and we make equal to the chemical potential. This gives us what is the characteristic healing length for a system that has some number of particles, a density of particles, and a scattering length. Because this is just due to interaction. Okay? to have a zero healing length, which means a wave function comes and boom, you need an infinite scattering length for this approximation. And that doesn't exist, really. I mean, you can have big, but... Okay, so, in fact, even in that approximation, the wave function will come and whoop, and this whoop is the healing length. And yesterday, Wolfgang showed vortices. And vortices, you saw the dark part where there is nothing there. So the wave function goes to zero there. And goes, you know, it should be like, choom, but it's not because of the healing length. So the typical size of the vortices is also the healing length. And this I put in quotation because I took out of a paper from Jean Delibard. They're going to be here. You can ask him. And if he say no, then he wrote wrong. Because the healing length is the typical length in which the superfluid recovers from a sharp change. Okay? It's written there. So I just import. So this is the concept of healing length. And you're going to hear also healing length many times, I hope. And you know now what it is. Okay? So let's see what else so we have. Nothing. And it's exactly 10:30. So I thank you very much for sitting here this morning. If you have any questions.
Thanks, Professor.
Thanks. Now, you may have a chance for a question before coffee. Let me tell you that the course that, you know, when I talk with them, I suppose to give you introduction to many things because you should hear about this before other talks. Okay? And Ketterle yesterday was very informal, gave a general, but now he's going to build up some more concepts on that. And of course, what I show you is present in all the presentations we see. So if you have any questions that I can answer, I'm not a theoretician. I don't solve Gross-Pitaevs every day, but I have people that can help me if I need. But you can ask a conceptual question. Maybe I can.
What you have in your pocket?
Is a present. Well, that's depend on the questions. That depend on the. This will be later. It's here. I can't. Oh, look. It cracks. It's wrapped in a present paper. It's not peanuts. No questions? Yes. Shh.
In the problem of the optical lattice. In the problem of the optical lattice that you solved, you have the optical lattice and you have an atom in each side, and you are going to turn off the lattice adiabatically, and you want to know what do you have to do in order to have a condensate at the end of the process. To end. But my question is, if you turn off the potential, you will not have any potential at the end, and you don't have any ground state to occupy macroscopically, and how can you speak about a condensate in that condition?
Good question. You see, normally we say that a free condensate is a condensate in an infinite box, and the approximation we do, which is the thermodynamic limit, we make the number goes to infinite, the volume goes to infinite, and the density is finite. So this is what I did here. But I consider that this macroscopic object is big enough that I can consider as infinite. Okay? And this is what people do in the lab anyway. So even though you have a free, it's still a particle with a single wave function behavior in a way that you expect a condensate to behave. And they produce this free condensate, and then they interact with part of it or with another condensate, right? This would be a kind of free expanding condensate, yes. So I used the other one.
So you will know that you have a condensate because you will observe that sharp distribution.
No, you start with a condensate, and you put all the particles in the ground state of that potential. If I have one particle there and I put the lattice down, this everybody knows that that's a condensate, right? Because you have all the conditions, the number of particles per cubic de Broglie wavelength is the right one and everything. Okay. So maybe he have an addition for me.
I think there's an additional trap. There is a harmonic trap in this case, or not?
No. This is just a free.
Just free.
Yeah,
Just
the way
the
you
outcomes.
can have that. You can turn
Just
off
the
the lattice
outcomes.
and have a, but you do the same calculation for the harmonic oscillators. Okay.
So you have just the optical lattice. You don't
Yeah.
have a
No,
a
here is an
harmonic trap in
optical
this case.
lattice that you adiabatically, slowly destroy, and we want to leave with a gas, which is like if I had a condensate in a potential and I take the potential away, I still have a condensate there.
Yeah, okay.
In fact, that's the way they measure everything. Almost nobody measures in situ, right, with the potential on.
I would comment that in general, cross-details is the non-local.
Ah, okay.
Locality.
Yeah. Oh, you want me to comment on?
Yes, it experimentally measures some non-local effects.
On the condensates? Not that I know.
But this I know dipolar condensate is
Yeah, well,
local effect should be important,
yes, non-local.
non-local.
Yeah,
Because
but
in
I-
general, it's not differential equations. It is non-local, non-linear shielding.
Yeah.
Cross-details.
I can't answer with some.
Because
knowledge.
all this equation with approximations that local interaction between two atoms.
That's right.
In general can be with some.
You understand the question? No. The way we, like the first part where I said in one point of space, the atoms interact with the local density. This is a local effect. But when you write the total wave function, in fact, one particle here, has a wave function that goes there, so this is a kind of non-locality type of effects in there. But I don't know how to answer if people has observed that. We are trying, São Carlos, to excite coherent modes of a condensate, which is the solutions of the Gross-Pitayevsky. And maybe, even though my hope is see effects that go beyond Gross-Pitayevsky, but maybe we can see, but I have to ask the experimentalists that are doing this all the time, and they can tell us. Okay?